Hello everyone, my name is Tom Ruminski, and I am pleased to talk to you today about one of my favorite topics in chemistry, and that is redox reactions. Now you might be looking at this PowerPoint and say, geez, that's an awfully boring looking PowerPoint. Well, my theory is that redox reactions are so darn interesting that any sort of a design or background would have just been a distraction and thrown you off from such an interesting topic. So let's jump right into it. First, give a few definitions. A definition of a redox reaction is any reaction in which the oxidation number of an atom or molecule is changed. Now, most of these reactions that you'll encounter, in fact, pretty much all of them, uh, will involve the transfer of electrons. That's how the oxidation number is changed. Oxidation number is just a fancy name for the charge on an element, or rather an atom or molecule. And the name redox comes from the two names reduction and oxidation reaction. In the case of reduction, a species gains electrons and the oxidation number is decreased. And on the oxidation side, there is a loss of electrons and an increase in oxidation number. And point at the bottom, there cannot be an oxidation without an accompanying reduction. Early on, scientists defined any combination of an element with oxygen as an oxidation, and as science advanced, scientists realized that when oxygen combined with other elements, the oxygen would gain electrons and form a -2, in most cases, a -2 ion, and the other elements or element would lose electrons and form positive ions. And so the name oxidation originally, combination of an element with oxygen, was called an oxidation, and that makes sense just based on the name. And so as scientists realized that there was more going on, transfers of electrons, the name sort of stuck to define any reaction in which a species lost electrons and became oxidized, not necessarily with oxygen. And on the other end of the spectrum, removal of oxygen to yield pure material was known as reduction, and the same case applies as with oxidation. The reactions can take place without oxygen but still be called a reduction reaction. So some general examples of redox reactions are metabolism of foods, the breakdown of proteins, carbohydrates, and fats will yield redox reactions. The most common and probably the most tangible example of redox reactions occur in batteries, which is our layman's term for electrolytic cells. Electroplating is a process where metals, or even in some cases plastics or other materials, are coated with a layer of metal, usually copper or zinc or other metals, to protect whatever material. And in all combustion reactions, there will be a redox reaction, most notably combustion of hydrocarbons. So let's move on to an example of an electrolytic cell. Like I said, probably the most tangible, real-world redox reaction that we can take a look at. And redox reactions, or rather electrolytic cells, can look fairly complicated, except if you look at this particular reaction, all we have is a reaction of solid copper in an aqueous solution of silver ions. And so the only difference with an electrolytic cell versus a reaction, say, between solid copper and silver ions, is that the reaction is split up into two half cells with wires and a salt bridge connecting either half of the reaction. So the only difference is if we put a bar of copper into an aqueous solution of silver nitrate, like we have on the right-hand side, the copper would form ions and the silver would solidify as a substrate. And that's the case here, except that by splitting the half cells, we're able to allow the electrons to move through a wire and use them to power a motor or a light or this computer that I'm recording this video on. And so that is how electrolytic cells work. And of course the salt bridge contains ions, which are usually in some sort of a jelly, and that allows the equilibrium to be maintained on either side of the reaction, allows for flow of the electrons. And so a few example formulas of redox reactions. A very real-world, tangible example is the formation of iron oxide or rust, where pure iron reacts with diatomic oxygen to form iron plus 3 ions, and combines with the oxygen to make iron oxide or rust. And you might be saying, well, iron can also form a plus 2 ion, so if that was the case, you would end up with FeO instead of Fe2O3. And through a little bit of research, I found that FeO in nature is a very, very rare occurrence. In almost all cases, if you examined a molecule of rust, you would see 2 iron atoms bonded with 3 oxygen atoms. And so the next reaction is the oxidation of ammonia to create nitric acid. Nitric acid is used in fertilizers. And the final example, another very tangible real-world example, is combustion of hydrocarbons. In this case, we have propane reacting with diatomic oxygen to form our standard hydrocarbon products, CO2 and H2O. And so I'm going to dive a little bit deeper into the formation of iron oxide, or rather the electrolysis of iron oxide. Electrolysis of iron oxide essentially, or rust as a layman's term, is essentially forcing the reverse reaction of iron oxide to break down the rust into its parts, iron and oxygen. Of course, this has practical benefits. If you have a rusty piece of iron or steel, you can use electrolysis to remove the rust, and that's exactly what I am going to show in my video. Alright guys, I'm now going to take you through using electrolysis to remove rust. So the idea is that rust is formed through a redox reaction between iron and oxygen. And the idea with electrolysis is we're using electricity to force the reaction in reverse to break apart those iron oxide bonds. And so to do this, first things first, safety glasses, rubber gloves. We also need something that's rusty to use. This is a metal file. It's kind of rusty. Yeah, you can kind of see it there. And so that's what I'll be using to test to remove the rust. We also need it's kind of hard to describe. It's called the Sacrificial Anode, and we're going to be using this piece of steel pipe. I polished it up to remove some surface rust that was on there already. And the idea is that the rust will transfer from the file to this, and I don't care about this, so it's no problem if it gets rusty. I'll explain a little bit more about that once I set up the reaction. This is called washing soda. It looks a lot like baking soda, and it's very similar to baking soda. Baking soda has a formula NaHCO3. Washing soda is Na2CO3. And the idea is that the Na2CO3, since it's a group 1A metal, sodium, will dissociate in water and allow electricity to flow through so we can get our electrolysis going. We also need some jumper wires for our power supply, some steel cable. I'm using steel because I tried using copper and my whole thing turned green, and I realized that copper oxide is green and it turned kind of gross and it was not fun. And so we also have just an old Cluck-U bucket of water and a power supply. This is a 10 amp 36 volt power supply, and I don't think we'll be using all that power, but we've got it if we need it. So now I'll show you the setup. Okay, first things first, I'm going to hook up the jumper wires to the power supply here. The leads are on the back, so I'm just going to use white for the negative lead and red for the positive lead. Okay, well I probably should have done this first. I'm going to mix in the washing soda into the water bucket. I don't have very much water in here. It's only enough to cover about half the file. That's so we can see the difference between the side that's had the rust removed and the rusty side. And so I'm going to mix in the washing soda.
It's recommended about a tablespoon per liter, or maybe it was per gallon. I don't know. Just add a little bit extra. Can't hurt. I've got plenty. I'm actually gonna put a paper towel over my power supply to prevent any splashes or anything. So now I just have to mix this in. So the two sodium atoms will dissociate, and so that will give us an electrolytic solution, which will conduct electricity and allow the electrolysis to happen. So that takes care of that. Alright, now we're going to hook up our anode and cathode. Our anode will be the steel pipe, and the cathode will be the rusty file. And so we're going to hook up the file with the cathode, which is the negative wire. And it's a little bit confusing because anions are negative, and so you'd think that the negative wire would be called the anode. But it's called the cathode because it attracts cations, which are positive. And so our sacrificial anode, the pipe, will get the positive lead, the anode, because it attracts anions, which are negative. And to connect this, I just used some of the steel cabling here, tied a little knot, frayed it out, and we'll put this in here. Make sure that the leads don't touch. So we've got our sacrificial anode hooked up to the anode, which is positive, and our cathode, which will have the rust removed, hooked up to the negative side, cathode. Okay, now comes the fun part. We've got our... I'll just detach the camera. Now we've got everything hooked up, our sacrificial anode and our cathode to have the rust removed. Just give you one more look at this, at the file. See how you can see how rusty it is. Kind of difficult to see in the light, but it'll be evident at the end when we look at the part that's sticking out versus the part that's in the water. And so now we are going to set up our power supply. This supply goes up to 36 volts and up to 10 amps. And we probably won't need all of that. I've had good luck at around 20 to 30 volts, and the amperage is very low. It's only about half an amp. And so first thing we'll do is we'll flip this on. As you can see, nothing's happening just yet. We need to give it a little bit of power. I'll turn the voltage up to about 24 volts. That's a good starting point. And just very, very slightly give it some current, about 4 amps. And let's see what's going on over here. As you can see, we've got bubbles on both the anode and cathode. These bubbles are mostly oxygen, because the oxygen, of course, on the cathode is being broken from the bonds with iron, so that's going to bubble up. And we probably also have some hydrogen gas because we are dealing with water, and passing current through water causes electrolysis of the water, which breaks down the hydrogen and oxygen bonds. So the reaction's going pretty steadily right now. We might want to crank it up just a little bit. Let's give it all the way and give it some more current. Crank it up all the way. What the heck? Now we've got some bubbles going, and so this reaction can be let go as long as it wants. It's as long as you want. It's a self-regulating process. So as soon as all the iron oxide on the cathode is run out, the reaction will just stop, and so you don't have to worry about anything blowing up or burning down your house. And so I'll let this go. It might take 10 minutes. It might take 2 hours. I'll just make some updates, and then we'll go from there. Alright guys, just wanted to give you a little bit of an update. It's been about 5 minutes or so. Yes, that is wagon wheel playing in the background. I'm busy out here in the garage working on my remote controlled truck, but anyway, just wanted to give you a little update. After 5 minutes, we've got some brown bubbles forming at the top. The cathode is still bubbling up like crazy. More bubbles around the anode, and actually I had to turn the power supply down a bit. Turned it down to running just over 20 volts or so, because I went to adjust the cathode and it was hot to the touch, and I didn't want it melting through that plastic. So that's all that's going on right now, and we'll maybe wait another half hour and I'll give it another check. Alright guys, just a quick update. This is the half hour mark. Yeah, country can only last me so long. I switched to Credence. Anyway, half hour mark. Darn, you can't really tell from the camera, but the rust is falling off. It's becoming lighter, and I can see some of the bare metal showing through, so we're gonna let that continue, and we'll check it again in another half hour or so. Alright guys, another half hour update. It's been a total of right around an hour. Take a look at this. You can't really tell through the camera, but metal's cleaning up. Let that keep going, and we've actually got quite a lot of heat in here. Got my infrared thermometer. Just take the temperature really quickly. And the outside is 110 degrees Fahrenheit, 44 Celsius. Let's try the pipe, 45. Yeah, okay, so the water's a good representation of the temperature. So we got a lot of heat going on through the reaction, so we'll let that go and keep updating. Another quick update, guys. The power supply is actually getting pretty hot as well. It's working hard. Let's check the temperature. We've got right here in the back on the heatsink, we've got 124 Fahrenheit, 50 flat Celsius. So 51, 52. It's probably 55 on the inside. So it's getting up there. Working hard. Alright guys, we're here at the 2.5 hour mark. The reaction is still chugging away. The rust is coming off pretty well. Hopefully I'll get some good pictures at the end to show you. And right now I'd like to talk a little bit about some rust prevention methods that are used on steel and iron. Mostly steel. Steel is just iron with extra carbon and other elements. Stainless steel has more chromium and other elements in it to help it prevent rusting. And so I just wanted to talk a little bit about some methods that are used to prevent rust on steel. First method I'd like to talk about is called galvanization. And right here I have a piece of galvanized steel. I think I got this at Home Depot. It was just a scrap piece. As you can see, I scraped off some of the galvanizing and left this outside for about 2 months, and it rusted over pretty readily. But anyway, galvanizing is a process where a layer of zinc is coated onto a piece of steel. And you can see here the zinc has sort of a speckled pattern to it. And here's a good spot. It's got a speckling pattern to it. This is an example of hot dip galvanization, where the steel is literally just put into a tub of molten zinc, and it deposits a very thick layer of zinc to help protect the metal. And I used a bench stone to sort of scrape off the zinc and expose the steel, and I left it outside for about 2 months to let it rust, so I'd have an example of this for the project. But there are a couple other methods of galvanization. There's only one that's really used, although hot dip is the most common method for ease of application, cost effectiveness. The other method would be electroplating galvanization, where the steel would be submerged in a tub of zinc ions in solution, and a charge would be applied, and the zinc would gravitate to the steel. And it's a little bit more expensive. It provides a thinner coating, which is good if you have moving parts or a lot of friction. You don't want that that zinc to be rubbed off too readily. But hot dip is most common. You'll see this on guardrails on the side of the highway. On those, the speckling pattern is especially evident, or on traffic light posts. You can see the speckling pattern, and so that's just used to protect the steel from rusting. The zinc. Sorry guys, I had to stop there for a second. Train went by my house and then a plane flew overhead and you couldn't hear me. So anyway, I was just about to talk about the zinc layer, and you would think that, what's the point of putting the zinc on there if it's just gonna, deteriorate anyway. Actually, zinc does not, zinc oxide and any other compounds that it would form while on the steel does not deteriorate at all. Within a few hours of the zinc being applied, it'll form some zinc oxide and zinc hydroxide, and ultimately react with carbon dioxide in the air, and after a couple of years form zinc carbonate. And that zinc carbonate forms the very outermost layer on the piece, and then underneath you have a little bit of zinc oxide and pure zinc, and then underneath that the steel. And so just by sitting out in the elements, the piece actually develops another layer of protection. So that's why galvanizing is a very, very common process for protecting steel. The next method that's common for preventing rust in steel is just formulating the steel such that it has rust preventative properties. And the main way to do that is to add a lot of chromium to the steel, because chrome doesn't rust, and chrome oxide that would be formed is completely colorless and harmless. And so a lot of your silverware at home, forks, knives, spoons, have a lot of chrome in them, and that prevents rust. Because you look at, this piece of steel I left outside, and you're saying, wow, that rusted like crazy, but my silverware at home doesn't rust. Well, it's because it's formulated a lot differently. More chromium, more carbon, different composition. Although you might be thinking that all steel should just be made like your silverware so that it doesn't rust right from the beginning. Well, the difference is that steel in your silverware is very, very weak. You could probably bend a fork or spoon right with your fingers, and if you tried to make a car out of that, it would just collapse under its own weight. Versus steel like this is very, very strong. This is carbon steel, and it's a trade-off. It's much stronger. Of course, it can rust more readily, so processes like galvanization are used to prevent it. And the next, just have an example here, is a ratchet. Obviously, it has to be very strong for working on cars or whatever. And this has, you can probably tell, it's kind of shiny. It's got a lot of chromium in it, so it has, it can be made properly strong, and the extra chrome helps to prevent rust. And the only downside with this is cost. Tools, high quality tools are very expensive, and so you have to avoid cheap tools that are going to rust or bend or break, and so go with good brands like, what is this? Snap-on, top of the line. The final most common method for preventing rust or damage to any sort of metal is to coat it with enamel or paint. Usually enamel is more common. Here's a ratchet box that I restored, just a ratchet kit, and I used Rust-Oleum pro-grade enamel. Spray this. I think it was about 2 or 3 coats. The old paint had sort of rusted through the enamel, and so enamel is great because it's looks like paint, and it could be considered paint, but the difference is that enamel goes on a lot thicker, and it's designed to prevent rust versus standard paint. Just is supposed to look good, but enamel is very tough. You can really, Rust-Oleum especially. Rust-Oleum is very well known and trusted brand. You can really bang on this and it won't scuff up too much or chip off. And so the advantage of this is ease of application, as opposed to galvanizing, because you can obviously do that at home. You can buy Rust-Oleum at Home Depot like I do. All kinds of different varieties. Here's just Pro Grade. Here is some engine enamel, which is good up to 500 degrees. I like this stuff a lot. And so you can do that at home if you have metal that you're trying to protect versus galvanization. Obviously, you can't just do that in your garage like I do with the enamel. And you can choose whatever color you want. It won't look, kind of unsightly like galvanization. And if you buy use a trusted brand like Rust-Oleum or Krylon, then it'll last quite a long time. Alright guys, one more process that's used for rust prevention to put a coating on steel or iron or whatever is called anodizing. Now, anodizing is a process where the part is submerged into a bath of ions, not necessarily metal or steel or anything like that, but just chemicals that will form a coating, and a charge is applied, and those chemicals coat the metal. What's cool about anodizing is that you can get in a lot of different colors to make things look cool. It can also be done to aluminum. Anodized aluminum is very common, although aluminum in itself doesn't rust or deteriorate quite as readily as steel, although it makes it look good. And the best example that I had of anodizing is my big old air rifle. And before everybody freaks out, these are completely legal to own. If you have any discrepancies, check the Second Amendment. But anyway, these are this surface here is anodized. It doesn't look all that impressive. It's just black. But the advantage of anodizing is that it's a very thin coating, which you might not think at first is good. But it's really right against the metal, and it doesn't scratch off very easily. It provides a great base layer for painting if I wanted to paint this a different color or add an extra layer of enamel. It would be easy to do. I would just rough this up a little bit with some sandpaper to allow the enamel to adhere a bit better. And it's also good in applications where there's going to be a lot of friction, and because it's a very thin coating, so it won't get in the way like enamel might chip off or rub off if there's a lot of friction in the area. But anodizing holds very well and won't chip off very readily with friction. Well, we're approaching the 3-hour mark here, and as you could probably imagine, watching this reaction go is kind of like watching paint dry, so I figured I'd entertain myself with a little shooting. Got my air rifle out here anyway. Let me just adjust the camera. Got a target out there. See if I can zoom in a little bit. That's just an old can of engine bright gunk degreaser. Used up the whole can on my remote controlled truck. And so now it's a target. If I can get the camera to stay in place. I've got the rifle in one hand and the camera in the other. And remember your firearm safety. I am wearing eye protection. So let's see if I can pop off this can. Shooting from sitting position. Oh, would you look at that. And as you can see, I hit the can a little bit left, but give it another shot. Alright, range is hot. There we go again. Alright guys, it's been a full 8 hours that this has been running. I took out the, well, I guess I'll shut it off now. I took out the pipe a couple times to scrape it off with the wire brush to free up some more space for rust to form. And that's about it. Just keeping an eye on the temperature and adjusting the power accordingly. Right now, 122. Okay, that's not that bad. Got up a little higher, closer to 140 before, so I had to tone it down. And I also went out to dinner, so I turned it down while that was going on. And just let it run. So let's see how hot this is. Oh, it's pretty hot actually. You can see the rust is gone. Looking a little dirty, probably all the stuff that's floating around in the bucket right now. So I'll run this under some water and clean it off, and we'll take a look. Alright guys, well here's the finished product. You can really see the how the electrolysis took effect. If I can get this to focus. There we are. See the clean steel here. Of course, this did take 8 hours, and the irony of the situation is that if I picked up this file out of the toolbox and said, oh, it's a little rusty, I should go clean that off, I would go over to my bench stone, which has a wire brush on it, and I'd clean this in about 30 seconds and be done with it. And that's probably what I'm going to do right after this. Actually, no, I'll bring this in and show you guys what the results are. But anyway, if you're going to do this yourself, right after you're done, you want to treat the bare metal with something. WD-40 is a good option. Everybody's got that laying around, or silicone lubricant, motor oil, anything. Depending on what you're using this for, of course. This is just a file. You could put motor oil on this and then wipe it down, and it'll be fine. But you know, the steel is raw now. It's gonna rust within a day or two. You'll see some surface rust pop up, and that might not be a big deal depending on what you're going to be using this for. But if you want to really seal it, you would want to treat it with something. And the electrolysis process is great because you can it works at the molecular level, works from the inside out, really, and so you know you're going to get every speck of rust off, or at least within reason, depending on how long you want to let it soak for, or how rusty the metal is. But it's good for small parts. Obviously, I'm just using a small bucket. You would need for bigger parts, you might need a bathtub or something, which isn't very practical. So you might, if you're looking to remove some rust, you might want to go with chemical method. You know, phosphoric acid is a very common rust remover, or some other commercial product for removing rust. And that is about it, so thank you for watching. Guys, one more thing, you know, at the end you want to clean up, make sure that you get everything. Oh, whoops. I hope that's not too bad for the environment. Nah, it's not bad for the environment. Iron oxide exists in the ground. A little bit of oxygen dissolved in the water. No big deal. Oh, now we're out on my front lawn. Look at that grass. Looks nice. I cut it. Just gotta clean this bucket off. My electrolysis bucket. Cluck, yeah.